Hello everyone, welcome to the third video of 10 AP Physics 1 summaries. Today we'll be looking at the circular motion and gravitation unit and focusing on conceptual review. If at the end of this video you're looking for more resources, please check out my description down below for links on more concept review and application problems. If you want to target your time towards specific content areas, I'll include timestamps in the comments for each topic. Let's get started. So this unit is actually looking mostly at circular motion and using gravitation as an example of circular motion. So let's start with defining circular motion. We're mostly working with uniform circular motion, which is the motion of an object in a circle at a constant speed. At all instances, the object is moving tangential to the circle. So you can imagine that if we have this ball, this tennis ball right here on this diagram, and it is moving clockwise, then at any instant its velocity is going to be moving like this, which is tangent or perpendicular to the circle. To get to the central idea in this unit, let's do a little bit of a virtual demonstration. So we have this group of people, and they have a tiny motorized toy car in between them. Let's say it starts here. And their task is that they are supposed to push on the car with the minimum amount of force required so that it continues to move in its circular path. What do? If the car starts here, then these two guys are going to push it this way so that it turns just a little bit so then it can continue to move this way. Similarly, these people will push it inwards, and when it gets here, they will push it inwards. All of this is so that the front of the car just turns a little bit so that it continues to move this way instead of driving out of the circle like this. They want it to keep turning, and so on and so forth. So what is the commonality here? All of the forces are pointing inwards towards the center of the circle. Let's use some proper terminology. So circular motion involves centripetal acceleration and centripetal force. If we look at the word centripetal, which was coined by Newton, we see centri, which is center, and then pater, which is to go after or seek out. So centripetal basically translates to center seeking. It's important that you understand how vectors work when we're working with centripetal motion because it can sometimes be confusing. If we have a vector like this, which is facing inwards, that could show that it's either the force or the acceleration because both are centripetal values. However, if we have something like this, which is tangential to the circle, this would be the instantaneous velocity. This makes sense because let's say we're swinging a ball above our heads and this is the rope that the ball is attached to. If we release the ball, then there's no longer a force that it is pulling it inwards, so it's just going to travel with the velocity that it had at the exact instant that it was released, which is this direction. The most important thing to understand with centripetal motion is that the force is center seeking. So at any location, let's say the ball is here, the vector would be facing the center. It is somewhat intuitive to understand that the force would be facing the center using the example that we saw earlier with the tiny car. And because acceleration is always in the direction of net force, then it obviously makes sense that the acceleration would also be centripetal. Once you understand the concept of centripetal force and acceleration in circular motion, then you're pretty good to go for the rest of the unit. Here are the essential equations for this unit. I will not be proving them out in this video, and I did find them pretty easily memorable as a student compared to some of the more complicated kinematics equations. The proofs do involve calculus, and then I believe that there are some with just geometry. So if you're interested, I will include them, but in general, I would recommend that you have them memorized just for timing's sake. The second equation is also pretty self-explanatory and you won't actually have to use it often, but you're essentially taking the velocity equals distance over time equation and applying it to a circle where you're exchanging distance for circumference and then time for period or the time that it takes to make one full revolution. So you're still doing distance over time, but you're doing it specific to a circle. So we see circular motion show up in a number of different ways on the AP exam. The first one is that they'll have some circular track and a car driving on it. And to key into the idea of a force that's constantly allowing it to move in a circular path or centripetal force, it'll ask what the friction that the car needs at a certain velocity to keep going this way without sliding, or it'll give you the friction and it'll ask what the maximum velocity it can travel at while staying in the circular path, which keys into the velocity component of the centripetal force equation. Next thing that it'll show up often is in loops in some kind of roller coaster situation, where the centripetal force is actually somewhat complicated here because the forces that contribute to it are different at this position and at this position per se. Let's say here, the centripetal force is what's bringing it down towards the center, which includes the normal force from the track, and also the weight force of the car. However, this would not hold true at this position where the normal force does bring it in this way, but the weight force would actually be drawing it downwards. So the components of the centripetal force vary at different positions on a vertical. The last way that we see it often show up is with planetary motion and gravitation. I believe that this is why they united circular motion and gravitation under one unit, because gravitation is such a good large-scale example of circular motion. This brings us into the next topic in this unit. There are three fundamental interactions that determine the structure and motion of objects, and they are as follows: gravitational, electroweak, and strong force. Sometimes people actually consider there being four fundamental interactions, where electroweak is broken into both electromagnetic and also the weak force, but the AP curriculum divides it into just three. Here we're really going to be focusing on the gravitational force. Of course, look at the other two if you're interested, but the main ideas are that every particle of mass attracts to every other particle in the universe, and that it obeys the inverse square law. There aren't really application questions on this topic, but it is good elementary knowledge to build upon so that we can understand the interactions that we're observing. You've likely heard of gravitation before, even if it's in a non-rigorous context, such as Newton watching some apple fall from a tree and going, "Oh my goodness, gravity exists." Obviously, this is a little bit hyperbolic, but gravitation was one of Newton's fundamental contributions to physics. Key ideas here: gravitational force is an interaction of masses, which means that it requires at least two masses. It is attractive, which means that the two masses want to go towards each other, not away from each other. This is the general equation that we'll be using, and it's important that you note that local gravitational field is approximately constant. So if we're working on the surface of the Earth, which most of our questions usually were, we can treat the gravitational field as constant, which means that if we have an equation like this, which involves the gravitational field or the G constant, we can usually just say G equals 9.8. Also note that while we're generally working with larger masses like the Moon and the Earth here, gravitation does occur between all masses. So even as an apple falls to the Earth is attracted to the apple with an equal force. This may seem strange that an apple is exerting the same amount of force on the Earth as the Earth is on the apple. However, the Earth is so much more massive that the force has very little effect. Because of the limits of this course, we'll only be considering spherically symmetric objects as sources for gravitational fields. In dynamics, we saw the concept of inertial mass, which is basically the idea that we can measure mass as a resistance to change in motion. For example, if we were doing an experiment and we wanted to experimentally calculate mass, we could manipulate a force on some unknown mass and observe acceleration with the idea of inertial mass. Here we see a second way of conceptualizing and measuring mass, that is gravitational mass. This is mass as a measurement of its gravitational interactions with other masses. An example of this would be as simple as using a balance scale, because you're relying on the gravitational interaction between the Earth and your mass. Let's look at three examples. So here we have three sets of masses. We have two pink, one blue, and two blue. In the situations with the pink, there are larger vectors, as we can see here, and when we have blue, there are generally smaller vectors. From this, we can experimentally assume that the pink has a larger gravitational mass than the blue, because its gravitational interactions are generally larger with other masses. Gravitational mass is used in this equation, Fg, or F weight, equals mg, with g denoting the local gravitational field constant. There's a classic trick question where you drop a marble and a bowling ball from the same height to see which hits the grounds first, and the answer is that they hit at the same time, given that we ignore air resistance. In this video, we see the same principle where there's a bowling ball and a feather dropped, presumably in a vacuum because the feather's just falling freely, and they do indeed hit at the same time, and this seems counterintuitive. You might be thinking, didn't we just establish that larger masses have more gravitational mass and the stronger gravitational attraction to the Earth? Why isn't the larger mass falling faster? This is a great question. It has to do with the equality of gravitational and inertial mass. Yes, an object with greater gravitational mass has a stronger gravitational attraction to the Earth, but it also has equivalently more inertial mass that impedes this motion. Masses to effects basically cancel out. And this is why, near Earth's surface in a vacuum, all objects fall with the same acceleration, g. One of the most interesting things about gravity as a fundamental interaction is how weak it is compared to the other ones, and you can see those ratios right here. However, it extends over an infinite distance, or it has an infinite range, whereas the weak force has a range of 10 to the negative 18 meters, and the strong force has a range of 10 to the negative 15 meters. Gravity, on the other hand, attracts all mass to all mass over infinite distance. However, because of the low gravitational constant and the inverse square law that gravity obeys, it feels so minimal to us. One helpful tool that we see when we're working with gravity is called a gravity vector field, where you have a field surrounding some object and you can visualize all of the tiny gravitational vectors that exist around it. So if you were, let's say this is the sun and you are some object in space at this location, you can use the vector field to understand what the effect of the gravitational field would be on this object at this location. This is particularly helpful if you have overlapping gravitational fields like the moon and the earth, because at any given location you can find the net vector value by just summing them. Vector fields are also experimentally helpful because by observing a vector field you can make conclusions about the objects or the sources that are causing them, and this comes up a lot when we make assumptions about outer space. Gravitational fields can be somewhat challenging to visualize, which is where the vector field model comes in so helpful. The biggest key takeaways are that the gravitational field is equal to the gravitational force divided by the mass, and that if gravitational force is the only force acting on an object, then the free fall acceleration will equal the magnitude of the gravitational field at that location, which is why we always see the free fall constant is 9.8. Okay, we made it. In my next video, we'll move on to energy. Thank you so much for watching, and be sure to check out the description for more resources and more about me. I'll catch you in the next one for more AP Physics 1 content.